today's title of the Tech Talk is Natural Language Processing for Event Discovery, Extraction, and Inferential Forecasting. This will be presented by Dr. Tom Danielson from Savannah Riverside. Dr. Danielson has received his PhD in Material Science and Engineering from Virginia Tech in the spring of 2016 and has an undergraduate degree in physics and mathematics. Dr. Danielson joined Savannah River National Lab in September of 2016 and is currently serving as a scientist in environmental science and dosimetry group. Dr. Danielson has played a key role in developing and executing deterministic models for groundwater contaminant transport for various activities at Savannah Riverside, including performance assessment at E-area, low-level waste facility, and D&D of 235F facility. For past several years, Dr. Danielson has been applying artificial intelligence, machine learning, and advanced data analytics in the area of contaminant transport, meteorological forecasting, and nuclear non-proliferation. Welcome, Dr. Danielson.
All right, thank you, Himanshu, for the introduction. I appreciate that. Really excited to be here today and looking forward to the interaction. So with that, as Himanshu said, I'll be talking about natural language processing for event discovery, extraction, and inferential forecasting. And in particular, I'm going to be talking about a project that we've been working on since about 2019. We started the fall of 2019. And so this was kind of a time before, every person on the street would know, what ChatGPT or something like that is, right? So we started that development, and we've been using sort of these embedding and language models across this time. And then suddenly we come to, late 2022, early 2023, and now everybody you would talk to would know about ChatGPT. And so needless to say, this has been one of the faster evolving fields that I've worked in ever, and it's also been one of the most interesting. So I'm excited to talk about it in the context of a couple of different projects that have been going on since 2019, and then also sort of some vision for where this could go in the future. So with that up front, I wanted to just say that I've got a team of people. We have a collaboration with Virginia Tech that started with the original project. We started working with them principally because they had this system that they had developed that was called Embers, and it was a forecasting system that leveraged social media and certain data from different apps such as OpenTable. And what they were doing was basically building out some planned protest type models. And so they were applying this in Latin America, the Middle East, and North Africa, and sort of using some of these signals to sort of predict when and where protests would break out at various times. And so we took that and we saw an opportunity for an application of similar techniques in the space of non-proliferation, nuclear non-proliferation. So this is essentially sort of monitoring activities sort of on a global landscape where people are trying potentially to look into nuclear weapons development efforts. And so we've had some success there. And of course, like I mentioned, we've got applications in mind for this across really across any application, but we're looking into some things in DOE-EM, continuing working with NNSA, the National Nuclear Security Administration, and really anywhere anybody can think of. We're happy for some input and ideas, and looking forward to that. Also wanted to mention Alejandro de la Naval was here over the summer, and he played a really key role in taking sort of a lot of our research level code that we had written that was kind of scattered throughout a bunch of different Jupyter notebooks and packaging all of this up in really a short period of time. So was really impressed with Alejandro. He did great work for us, and it's going to be really key going forward. So wanted to kind of mention the team members up front here. So with that, we'll get into the background and goals. So again, we started this project in fiscal year 20, so the fall of 2019, develop a prototype system to extract events of interest from open data sources. And when we started this project, we had this really sort of interesting and unique vantage point sitting here on the Savannah River site where we had this new mission that was coming to SRS. And so this was the pit production mission. So fabricating plutonium cores for nuclear warheads. And so This was just coming into fruition as of about 2018, so we were, a year ahead in time. But we figured we could probably go out and start to collect, open data sources to look into whether or not we could extract events of interest and then potentially come up with some sort of inferential forecast where we could essentially detect that the pit production mission would come to the Savannah River site prior to any official announcement. And so like I said, that official announcement came out in May of 2018. And we had sort of a very interesting result in early on in that work where we said, okay, we have these text-based data sources. We're going to apply we're going to train word embedding models, and we're going to do this on a temporal basis. And essentially, we're going to see what kind of signal we might be able to extract from that by looking into sort of the context of words and how that shifts across time. And so just right up front, wanted to highlight one of those results. So looking at pit production in Savannah River site, we can look at things like the cosine similarity of these terms as we train different embedding models. And so each one of these dots would represent an embedding model. And what we actually found was that the similarity rank for Savannah River site to the term pit production as of that point in time was actually most similar as of March of 2016. So again, keeping in mind that that official announcement came out in May of 2018, we were about 2 years ahead of time, and with this sort of light indicator, so to speak. So this was great. It gave us confidence in the models and in the technique. And since that time, we've been working really hard to sort of continue on in building this out and making it something that's very usable for anyone who's interested. And so in FY22, we were funded basically to prove the translatability of the pipeline, applying it to worldwide semi-restrictive data environments and also a more broad domain. So pit production at SRS, very specific activity in a very specific location. We wanted to now take this system, which is looking at social media, a Twitter data set, as well as sort of a broad internet archive, looking at news articles and blogs and even job postings, things of that nature. And we wanted to look at that on sort of a worldwide scale and then apply this to civil nuclear energy. So sort of getting an idea for the landscape of different activities that are going on. And I'll certainly lay that out a little bit more here in a bit. But ultimately, what we want to do is make this prototype system and really be very efficient at returning and extracting maximally relevant, minimally redundant information in an actionable time frame for those who would use it. In addition to that, we want to have some sort of, again, sort of inferential forecasting capabilities. So there's a lot of different models for that. Even these sort of, like I said, light indicators that sort of are pointing you in a direction that you can sort of chase down a little bit more. Just a project at a glance, we're looking at, again, obviously natural language processing, large data sets, millions of tweets, millions of articles, maybe custom data sets. We want automated information extraction. We want some inferential forecasting capabilities. And then, of course, what we're also working on is some human guided sense making. So you have all this data, you have these temporal models. It's tough to see what exactly might be going on under the hood. A user would need to be able to sort of interact with this and sort of make some sense out of it and potentially even explore their own hypotheses. So in terms of the intended use cases, we really see two very good use cases here. So we have sort of the real-time streaming environment, okay, so where you're basically monitoring data streams for events of interest as maybe they come in. You can identify and sort of track along with the trajectory of events, and then potentially this allows you some inferential forecasting capabilities using maybe some things like generative AI or other techniques. And this, again, it can be automated or it can be human guided. So as someone is sort of tracking along with their data model, perhaps they can give input and sort of refine it as it's moving along to sort of fine tune and better understand sort of, again, that trajectory of events. In addition to this, and where we've sort of probably done the most testing at this point in time is on in sort of the historical data set paradigm. So looking at a historical data set, so what I'll show you here today, we're dealing with about 8 years worth of data and sort of understanding the trajectory of events across time. So as if an analyst was pulling in all the data that they possibly could and then wanting to find sort of key milestone events that had happened along the way. It sort of brings them up to speed and allows them to sort of understand what it is that they're looking into. So they'll see sort of these key points of change throughout time and all of the events that would be associated with those. In terms of sort of the opportunities here to think about, and certainly something I'd be interested in talking with anyone, a little bit more about, is this is just kind of a simple um, uh, diagram showing sort of how we're thinking about this. So of course, initially what we've been doing is all been text based, but we want to leave the door open for sort of multimodal data fusion, whether that be you have your own numerical model that you're running that can supply some information to this existing pipeline, or whether that be bringing in things like audio and visual type data sets as well. There's sort of endless possibilities in terms of how we're thinking about this, because we can essentially treat each one of these data sources separately. We could also treat them together, but we've been primarily treating them separately, running the different models on those, as some models might work better for certain data sources than they will for others, and then sort of on the back end fusing the information that comes out all together, so that we can apply or give a forecast or alerts or whatever it would be that we're interested in. All right, so taking the pipeline that I mentioned about pit production at the Savannah River site and translating it over to civil nuclear power. So to sort of understand what that looks like, you can think of this in sort of a very high level ontological way, where you've got sort of the universe of nuclear activities that are going on. And then from there, you might break that out into sort of two subdomains where it's weapons and other, right? And so weapons activities are all sorts of different things. And ultimately you get down here to fissile core fabrication, which was the pit production activity. On the opposing side, and where we're currently looking on the civil nuclear power side, you come down to nuclear power. You might also have things like medical research and industrial type activities that are going on, and then you come down to civil nuclear power. Right, it's not a non-military use, where there's also nuclear reactors on things like submarines and other places. And then ultimately, when you look at civil nuclear power, you'll have different phases of activities that are going on. Right, so you've got the planning, the construction, the operation, and the shutdown. And so taking this system and applying it on sort of this worldwide scale, we have to sort of recognize that in order to capture good data sets and be bringing good data sets in, these are sort of the types of things that we're going to want to be able to capture and model on. So we have a very good use case in terms of sort of these state-sponsored civil nuclear power activities. So, for example, Rosatom is a state-level contractor in Russia. They are building reactors in a number of different locations, so places like Turkey, Hungary, Egypt, Finland, at least formerly. Again, sort of throughout the course of just this project alone, there's been an evolving geopolitical landscape that we've seen in terms of, uh, Russia, as well as some of these places where they were building nuclear reactors. And so there's this kind of constant geopolitical push pull in terms of what's going on that we can sort of track along with and sort of understand how that's changing the dynamics. Fortunately, I guess if you're looking at Rosatom as the contractor, they have a pretty specific type of reactor that they specialize in constructing in locations. But of course, again, we're sort of open to any type of nuclear reactor there might be. But if this was going to be our case study, we'd definitely be looking into the VVER type reactors. And I guess I'll just mention again, so we had 8 years of data, and that's spanning from 2014 to 2022. And again, we're using Twitter, and then we collected data in terms of, like I said, kind of a broad internet archive from newsapi.ai. All right, so still in the background here, haven't really talked about much of the mechanics of the pipeline yet, but building out sort of this case study and sort of how we can test our pipeline and understand sort of its performance, what we did was essentially start to manually create sort of a timeline of events. And so that's what's being shown here. So essentially we said, okay, if we go to Wikipedia and we look into, different locations or different activities that are going on in these various case study locations, where Rosatom in, say, Turkey, for example, who's building a reactor called Akuyu, we should find in probably the first paragraph some event. And if it's in the first paragraph on Wikipedia, it's probably a fairly high profile event that had happened. And so at the very least, our pipeline should be able to capture that very quickly and be able to pull that out of the data set. And so you can see we've got sort of a broad number of, scope and different types of events that have gone on. So launch ceremonies and equipment deliveries and contracts that are being signed between the two countries and all of this kind of stuff that we wanted our pipeline to be able to capture. And we want to be able to do it within pretty close proximity in time to when it actually occurred. All right, so the whole pipeline is basically built on this idea of being able to look into how the meanings of words change. So our data sets are text-based, they're telling some story, or it's someone's feelings or something like this, right? And the language that they're using essentially can change if there are sort of these repetitive motifs and things of that nature at certain points in time, and then that shifts a long time as it's used in different ways. And so we have this idea of sort of having temporal shifts in the context or the meaning of words. We have cultural shifts that occur. Millennials versus baby boomers might use a slightly different vocabulary when they're talking or tweeting or doing things like this. And then, of course, we've got linguistic shifts. So looking at things like British English versus American English and sort of understanding some of the differences that would be used there. And so we can think about a couple of good, examples where we have like Apple. So if you go back to 1900, an apple would probably be most exclusively meaning the fruit, right? But as we sort of fast forward into, the 1980s, 1990s, and the 2000s, Apple is this sort of emerging, rising, and ultimately sort of dominating technology company. And now the word Apple, if you say it without context, both the fruit and the computer company would probably come to mind. Similar situation with Amazon, right? And so we've got some sort of rules, basic laws, quote unquote, of semantic shifts. So looking at how the meanings of these words change, we can understand some things based on sort of the frequency that the word is used, as well as say the number of definitions that words have, or they're part of speech. So looking at verbs versus nouns, these might change more than what adjectives would. And so these are all sort of fundamental concepts that play into sort of what we're looking at here. All right, so looking at the pipeline. So how we basically operate on this is we start out with a set of SME defined key terms, and we use that sort of loosely. We have some automated schemes for being able to go out and define these key terms, basically scrape some text and post process it, and now you have a pretty good set of terms. This is also that you can go out and make a data pull to your data sources. So of course we sample the databases, we pre-process the text. So basically doing things like tokenization and lemmatization, removing stop words, potentially removing numerical information, and getting this down into a form where the text almost becomes a little bit unrecognizable to a person, because you're removing so many of these words like and that might have very little meaning in terms of actual context. And then we train our temporal language models. So again, this is using word embedding models, and actually in this case we're using just simple word to vec algorithms. So a single layer neural network. And essentially what this is allowing you to do is predict a word given context or context given a word. But really what it's doing is it's looking at all of the language that you're feeding into the model, and it's learning a vector representation of the words. So now what we're able to do from there is we're able to compare a word from a time slice and a subsequent time slice, and we're able to compare those two vectors using metrics like cosine similarity or something of that nature, and we're able to see how different its contextual use was during those two different time windows. And if we see a large enough change, potentially you found something that would be like a contextual inflection point or a contextual shift in those keywords and phrases, which then acts as an indicator that an event of interest might have occurred, that the conversation has changed around a specific key term or set of key terms, and that probably we should have some techniques that go in and sort of extract what events actually occurred during that time. And so essentially I have this shown as sort of a feedback loop here. And that is again, because if you can think of this in sort of the real-time streaming environment, you might want to update that set of key terms across time. So you start to learn new language that's coming in, and you might want to start pulling a little bit more on some terms that weren't initially included. So so this model can be sort of self-updating as you move along and as you operate it. So I mentioned that we have some automated techniques for being able to create sort of these key terms and then go out and then actually acquire the data. And so in the case of the civil nuclear energy, what we did was actually go to the country profiles from the worldnuclear.org website. and essentially they've got, all the countries that are listed on there. We went into each one of those web pages, we scraped all the text, we extracted the noun phrases, we post-processed those down to sort of a reducible form. So if you think of, for example, National Nuclear Security Administration, you could get all of the data that would be associated with NNSA by just having nuclear security as one of your key terms or key phrases. So we do post processing in that regard. And so our pipeline essentially takes, about 70,000 starting terms, again, noun phrases, and it post processes them down to about 450, 500 key terms where we can actually place the data queries. Again, this is a very transferable technique. All you need is sort of a seed document set or seed text base. In the PIP production work, we use things like the environmental impact statements and things of that nature to be able to create sort of this vocabulary. And this essentially allowed us to pull about 7 million articles and about 7 million tweets across this 8-year time frame. So these query terms, they're mostly nouns. There's some adjectives and verbs, but very predominantly nouns. And so I mentioned already sort of the reducible form, but we also sort of enrich our query terms with some Boolean logic as needed, where we would say enrichment, for example, this can be educational enrichment, or it could be uranium enrichment. And so in some cases, we add sort of some Boolean logic there to make sure that we're focusing in on the domain that we really want. So we would add something simple like and nuclear. And again, essentially, we're looking to track or capture semantic shifts across single terms or many words at once. So we can do this in sort of multiple different paradigms if there's, a specific area of interest. But we're looking for events essentially. Something that would look like this. This is totally generic, but Rosatom enters cooperation agreement with the new country, and so then its context has essentially shift. We want to detect when that new country pops up from the previous time periods when that cooperation agreement did not exist. All right, so getting into the data sets a little bit. All right, so again, Twitter and Broad Internet Archive. So just on the top and the bottom, just showing you sort of how the number of articles changes across time, articles and tweets. You can see relatively consistent with some slight upticks here that are going on. It's a log scale on these particular plots, and it's sort of gradually increasing up to about that 7 million number. On the right-hand side, it just gives sort of a snapshot in our case study examples of sort of the cumulative number of tweets containing one of the key terms where we might be interested in. And so I'll just zoom in on this real quick, just so you can see a little bit better. We've got Turkey and an accompanying reactor that's being built in Turkey, Akuyu, Egypt, and accompanying reactor in Eldaba, Hungary, and its accompanying reactor Pax, Finland, and its accompanying reactor Hanhikivi, and then of course looking at things like Russia and Rosatom, so on both data sets. So zooming back out, you can see that sort of already from this, you can sort of start to get some ideas about how much representation there is. These are cumulative plots, and so if they're flat, it basically means nothing new is coming in. And so you see sort of various jumps up in time where you have sort of spikes in what's actually being talked about. And so this is sort of kind of that challenge in looking at sort of this worldwide domain where all different things we're trying to follow are having events occurring at different points in time, and we need to be able to capture all of that and sort of dampen out some of the noise that might be associated with some of the different things that are happening. All right, so a little bit more on the data set. So looking into things like co-occurrences, again, looking at those reactor and country pairs here, this again just sort of highlights the points in time where the topics or those articles or tweets that were coming in are actually associated with, Rosatom or Russia. And so again, just kind of gives you some idea of how the events are unfolding. So you can see Eldaba, for example, did not have very high representation in our data sets until around 2018. And that sort of lines up with the reality of the situation as well. All right, so the overall pipeline. So this is really small, but essentially what the point is here is that we have sort of at the top level, what we're working with are these diachronic word embeddings or time-dependent word embedding models. And then we come down and we have a whole bunch of different analytical techniques that we're using to process those the outputs from those trained language models that are across time. So we're looking at things, different clustering techniques. We're looking at PCA, and then also some interactive aspects of using dimensionality reduction techniques. We're looking at the different cosine similarity operations, again, so we can identify sort of points in time related to one key term or related to multiple key terms. We're using sort of some graph-based approaches where we're looking for anomalous edges, or maybe we're recomputing sort of the embedding vectors and sort of comparing them across time. And then we're looking for sort of contextual inflection points ultimately. So what's shown here. So we're getting sort of these temporal profiles, and ultimately we're able to look at this again on sort of that single word or multiple key term type level. And again, all just to get a point in time where we think something has changed. And then once we think something has changed, we come in here and we start to get into our information or event extraction. So we've identified our point of time, and now we might want to pull out, specific sentences. We might want to generate events in sort of an extractive or abstractive type of way, so that we can understand what exactly is going on. And then we want to fuse all of that information together so that it's readily retrievable for whoever would be using the software. So kind of three key places that we're looking into here. All right, so if we start to try to extract insights from the time dependent models, one thing I wanted to highlight right up front here, and of course you can't read these key terms that are on here, but what you should notice is that essentially there's some that are shown in sort of magenta, and there's some that are shown in blue. And so this is basically the trained embedding models for various different points in time as we move through time. So we're at January 2015 in the top left. You'll notice that all of the red terms are sort of spread out, somewhat uniformly across some of the other key terms that are shown in blue that we're not as interested in. As we come over to June of 2015, you notice that suddenly many of those key terms, the red key terms, have started to cluster up. We still got a couple of stragglers that are out here. And you kind of notice that as you move through time, these representations are changing slightly, right? So it's a PCA plot, but these are 100-dimensional vectors that we're showing in 2 dimensions. But you're still able to sort of identify that the morphology, the overall morphology of how these vectors are distributed is changing across time. And by the time you get down here to the bottom right picture, you notice that there's a pretty nice tight little cluster of those key terms in terms of what's going on. So that tells us, first of all, that maybe there's some similarity in terms of the events that are happening there. What I will point out, and what you can hopefully see, is that we have the reactor terms that are up here, as well as some of the countries, and then over here you've got Russia. And so what you sort of start to understand is that these are very focused key terms, right? We're focusing on sort of the nuclear aspects that are going on there. But as a result of pulling this information all in together, terms like Russia are used in such a much more broad context that it sort of stays further away from those more specific terms. All right, so we've got our data sets, we've processed them, we're training our embedding models, and we're starting to look for contextual inflection points and start to sort of identify when things are happening. So in the pit production work, in our first iteration, there's so much development that has to happen in terms of not just training the models, but then sort of the information extraction aspects. And so we haven't done a whole lot of hyperparameter optimization here for this overall pipeline. We're looking into that, and we're working on that. But essentially, we kind of just picked a number based on sort of how we thought the data was coming in and what we thought would be fairly good. So um, we have sort of 2 different paradigms that we can train in. So we can train with sort of a 30-day growing window model. So you take 30 days of information, you train an embedding model, and then you add another 30 days. Now you've got 60 days worth of data, you train another embedding model, and so on. And then the other paradigm that we've used is, of course, a rolling window model with a constant size, and that might overlap a little bit with one of the previous. So we have a 180-day, 30-day rolling window model that we've also used. So again, constant size, but you drop a little bit of data and you add a little bit of data with each successive window. All right, and so again, this relates back to that very first plot that I showed, where we're looking at sort of the similarity rank across time. On the left-hand side, you're looking at Twitter. On the right-hand side, you're looking at news, and this just sort of gives you an idea of what these similarity profiles sort of look like. So we're looking at Rosatom and Akuyu here, and I'll kind of focus on this test case of Rosatom and Akuyu as we continue going through. But what you notice is that we're tracking on the total occurrences, and we're also tracking on the total co-occurrences with the term Rosatom as we move along. And so you see that sort of there's these jumps up. We saw this before, and you're noticing that when you have these jumps up in time, you also have a growing similarity rank. So lower similarity rank is better. It basically, essentially, it means, if we're at 10 to the minus 2, you're in the top, 1% or so of the overall vocabulary that you're looking at. In fact, about the top 0.1% of the vocabulary um, is the similarity there. So that's sort of how to interpret that y-axis there. And so as we look at like several different of these use cases, you notice fairly similar things, especially with the growing window model. Akuyu, it sort of comes down here and it kind of converges and levels off. When you're looking at Eldaba, which didn't have near as much representation sort of early on in the models, as it sort of ticks up, that's when you start to get your higher similarity. And then ultimately over here on the very right hand side of the plot, where we had a significant uptick in the co-occurrences, you start to see a much higher similarity rank. On the news side, where we again have this sort of rolling window, you notice it's a little bit more chaotic, but sort of you see some general similarities in them. So Akuyu is generally very high similarity rank with Rosatom all the way through time. And Eldaba, you see, is kind of increasingly, growing in its similarity as we move through time. And then just a couple of other cases. So essentially showing you Russia and Pax, again, Pax, the reactor in Hungary. What you notice is that you have sort of this initial high similarity, and ultimately it almost drops out altogether, where you're up at 10 to the 2. So you're like in the lower portions of high similarity with the term Russia. So probably an indication that not a whole lot would be going on there. If we look at Rosatom impacts, however, what you'll notice is that we have fairly high similarity the entire time. And then again, on the news side of things, again, much more oscillation that's going on, and you sort of hit these peaks and valleys of that similarity rank as you move across time. So these are good plots. They give you sort of this qualitative idea of what's going on in your data sets, but they don't give you much context. And so that's where our next sort of steps are. So I mentioned that we have sort of these network graph-based approaches. And so essentially what this is doing is building out a graph. So if the top level is this blue circle right here, it would represent a key term. Let's take, for example, Akuyu. And so what you can do from there is you can say to your embedding model, all right, give me the top n most similar terms. So these orange terms would be the most similar words in the embedding model to the term Akuyu. And you can do this, you could build this out as far as what you wanted to. So these yellow circles are the most similar to the most similar terms, and you could keep going with it as you wanted to. And then what we can do is we can actually build in some information about sort of the frequency of terms. So we might be interested if something has just popped up and it has a fairly low frequency, it might actually be fairly relevant to us. And so we can sort of tweak the weighting and give that a little bit of a higher weight in the overall recomputation of that vector. We can also look at things like the similarity rank. How similar is it to the key term? And if it has very high similarity in the context that it's used, it should be weighted higher as well. So we're slightly nudging these embedding vectors just to try to build in some of these more higher order interactions that might be going on. And then what we can do from there is we can use a handful of different techniques. Having a graph, now we can use things like Jacquard similarity. So essentially what came into the vocabulary, or what came into the high similarity levels of the graph, and what went out of them between two successive time periods. In addition, we can look at things like cosine similarity and Euclidean distance, because again, these are vectors that we're dealing with. So you notice here that, basically we've taken the ensemble approach. How many nearest neighbors do you use? How many ranks do you use in your graph? We've just done this across a whole bunch of different sized graphs, and then combined the end result all together looking at it. So not only across the ranks and the nearest neighbors, but also across the three different techniques. And so what you're seeing on this right hand side here is a similarity profile using each one of the metrics, but we're just displaying one rank and 10 nearest neighbors. But we have computed it across many different ranks and many different nearest neighbors, and what we've ultimately spit out here is these black lines that you're seeing. So that's merging all the information together, forbidding anything from having two successive inflection points right next to each other, and then ultimately plotting that point in time or selecting that point in time as where an event has potentially occurred. And it's pretty easy to see, I guess, as you look at this, that, if you look at Jacquard similarity, the graph for Eldaba changed pretty significantly here right around that February, March of 2018 timeframe. And if you recall back from a few slides ago, this lines up pretty well with how we saw the information actually coming in for Eldaba as well. We didn't see a whole lot of information until about February or March of 2018. So good alignment there. All right, so now we're sort of honing in on, with multiple different techniques, having points of time where we think something has happened, or where the modeling pipeline thinks that something has happened. And so then we start to move into the event extraction aspects. And so I showed you that timeline sort of in the beginning that had a whole different array of events that had gone on. And now I'm showing that again. So this is kind of our baseline capability here. So we've colored this based on sort of the time to detection. That basically anything that's shown in green would mean, we caught it within a month. And if you think about, again, sort of the hyperparameters that I mentioned, the window sizes, the rolling lengths, all of these kinds of things, how much data you're adding, 1 month is sort of our theoretical limit here. So if it's green, that means we caught it as early as we possibly could. If it's blue, that means we went out 2 months from the time that the actual event had happened, and then orange and red are 3 months or greater than 3 months. So you can see there's a good amount of green that's on here, and everything is colored. So that means that we happen to catch every event in both data sources using this pipeline, and we did it with fairly good performance, and especially when you consider that we didn't do any tuning of those two very key hyperparameters. So the key aspect here is, I guess, if you think about things like Eldaba is fairly low signal, and especially going into 2018, there was almost no signal for it, and then it sort of slowly trickles in there. So, these window sizes and how much data is potentially drowning out some of the information there. That's really a key thing to sort of look into with that. Taking a little bit of a deeper dive, like I mentioned, wanted to use the reactor in Turkey because we have really great representation for what's going on there. But first, I guess what I'll mention is that we've captured sort of these inflection windows. That was these similarity profiles and the black lines that I had shown previously, and we can do that across all of the key terms in our vocabulary, and then we can sort of build out this inflection windows matrix. I've been told this looks a lot like a crossword puzzle, and I certainly admit that, but our focus here wasn't necessarily on the graphics as much as it was on having sort of that raw signal that's coming out for us to take a look at. So what you'll notice is that you can look at this in sort of a horizontal sort of paradigm where you're looking at just a single key term and you're saying, okay, Turkey had an inflection point with this black square at January of 2015. Or you could look at this in more of sort of the vertical way, right? And you could say that Akuyu, Egypt, Eldaba, Pax, and Russia all had an inflection point here at February of 2015. And so there's kind of these multiple ways that you could potentially treat this. But essentially what we're doing in the case of looking into Akuyu a little bit further is we are taking each one of its inflection points, and then what we want is to have some technique that can go back in and extract what information is actually relevant. And so we're using things like transformer-based models, BERTs. You can also do this on sort of a method where you take our graph-based approaches and you compare those vectors with different sentences that are within the models, and you can extract things in that manner. And so as just sort of a test, again, with 7 million articles and 7 million tweets, what we did was we essentially said, okay, how about we have the model extract the information, and then we're going to manually post-process it into this nice form and just see how long that would take for a single person to do. And so what you can imagine is that there's tweets and there's retweets. There's a lot of different redundant articles that are being, posted. And so when you find an event, the information that comes out is still pretty high volume. You can be talking like tens of thousands of tweets or news articles that you're looking at. But we were able to distill that down to something of this level in just a matter of a few hours time. So it still significantly increases a person's ability, even if you're not able to get these very succinct and accurate summarizations that come out. But we're continuing to sort of work on the summarization automation aspects as well. But this was an extremely interesting use case because you can really see that the contextual inflection points line up with changes in what's actually happening in the data sets as well. So in 2015 for Akuyu, we were looking at a lot of protests that were happening within Turkey of this nuclear reactor, and particularly looking at the environmental impact assessments. And people didn't necessarily feel that it was safe or trust the environmental impact assessment that had been done. And so this assessment was approved in December, just prior to Putin to paying a visit to Turkey. Everyone was very concerned about the earthquake risk. This has suddenly become relevant again because within the last year or so, there was a very major earthquake that occurred in Akuyu. So the residents had definitely some grounds to stand on there. As you continue to come down, you find things like the EIA, the environmental impact assessment had actually been found to be forged. There were all these court cases that came on. The protests and sort of the government propaganda to the citizens started to play out, and we were picking all of this up. But they continued on with the building of the reactor. There was a groundbreaking that occurred. And as you sort of look down through here, you just continue to start seeing things like some of the geopolitical push-pull that I had mentioned. So if you think about places like Syria, Russia and Turkey were on opposite sides during this conflict in Syria, but then they were working together on these nuclear reactors. And so there were things like Turkey shot down a Russian fighter jet during some of the conflicts that were going on over in Syria. And so again, this conflict and this geopolitical push pull is really interesting. And then by the time you get down here to 2020 or so, we're seeing things like reactor pressure vessels are arriving for the first unit. You're seeing circulation pumps shipped to Akuyu. You're seeing all these material receipts and kind of really able to very well track the progress of what's going on at the reactor. All right, so wanted to just touch on this briefly. So this is taking a look at sort of the more vertical paradigm. So if you look at this is the inflection windows matrix, and you'll notice there's a very small number, and there's some color scheme here that's showing. So if you look at it in the horizontal way, of course, you see these colored squares that are coming across. Those are your inflection points for that single term, and then the way that these are colored is based on sort of the vertical paradigm. So lighter indicates that more key terms had an inflection point at that particular window. And so as you scan across this, you can sort of see some points in time where you have a very light areas. So I've highlighted that here in Windows 41, 42, and 43. And so what we noticed here was that 66 key terms had an inflection point between time intervals 41 and 43. This was around sort of the May of 2018 timeframe, early 2018, I believe. And what you find is that 85% of the tweets during that time period had the term national security, and they were related to primarily high-profile investigations that were occurring sort of at the top levels of the government. So think about the Trump investigations that were happening and the number of times that the word national security would have been used. This caused sort of a cascade effect or something of that nature across all of the language in our embedding model, or a very large portion of the language that was in our embedding models, and we were able to see this very well. So we can pick out sort of these more minor events on a single word type level, or we can capture sort of these more macro scale events that occur as well. All right, so I'm kind of getting close on time here, so I'm going to go a little bit quickly through this. But essentially, what we're interested in is looking at some of these dimensionally reduced forms and understanding how this changes. So this is very similar to those first plots that I was showing, where essentially the PCA is changing across time, and so you can kind of see that things are moving around as you're bringing in different information. So we're exploring things like cluster analysis. We're looking at cluster membership as well as what's leaving clusters and maybe going to a different cluster. We're looking to see if we can explore sort of summarization of different clusters. Each word is associated with documents, several documents in many cases. And so we can look at things like pairwise movements between terms. We can sort of understand which words are sort of working together, or what's the push pull look like in our actual data sets, what new information is coming in, and how is that impacting what's going on. And we can also explore this embedding space by looking at things like tweet vectors. So in this case, what we're doing is basically taking the arithmetic mean of every word that would be in a tweet, a single tweet, to come up with a tweet vector. We could also train, of course, models on tweets and using something like Doc2Vec or something of that nature. But in this case, we've done just the simple mean. And then you can plot those tweets based and color them based on the key terms, and then you can sort of look at all of the tweets that are in a specific window, and you can sort of start to understand how the tweets or the topics are sort of overlapping with one another. And the key thing here, I guess, to take away is, again, that morphology is changing as you move across time from sort of the top left image over here to the bottom right image. So what we understand is what's overlapping with what, and what new information has come in that's caused sort of that overlap to change. And so we have some techniques for looking at that. So we can look at, say, for example, in this particular case, Russia and Turkey. So you've got Russia shown in blue and Turkey shown in orange. And so these would all represent tweets here, and this is just, again, a PCA plot of those tweets. And then we can plot sort of convex holes surrounding sort of each one of those tweets. And what we find is that we have sort of these overlapping regions of convex holes that capture tweets from both Russia and from Turkey. And so the theory here is, of course, that whatever's in that overlapping region is what we're probably most interested in if we're interested in exploring sort of the interaction between Russia and Turkey. And you can see, of course, that changes across time. And you see down here in model 9, we saw, pretty good overlap, and we saw a lot of information from both sides that came in there. And so we started looking into that. So of course, we're seeing a lot of information about the start of construction of Akuyu, and we kind of keep going down, and good information, very relevant to the topic. But we also found that in here, we found that that Rosatom was essentially looking to start building reactors in Nigeria. So we got sort of this information that we weren't necessarily looking for that came out. So we decided to pull that thread, and we started looking into, okay, so Russia and Nigeria. This is a new one. So now Nigeria is shown in orange. We do the same, we use the same technique. And again, you come down to model 9, and you've got sort of this explosive action that's all of a sudden going on, and a lot of information from both sides. So we go down, of course, with the same train of thought. We do see, of course, that there's information about Russia wanting to build some reactors in Nigeria. And then we also found that they were looking to build power plants in Argentina. So pretty interesting how that can sort of lead you down a certain path of what's actually going on. All right, so that's kind of the pipeline as it stands. We continue to work on this, again, really on the information extraction standpoint. We want sort of, again, maximally relevant, minimally redundant information. We want sort of these high level summaries. We want to automate that to an extent, or we want to provide access as well to sort of the full data. Thinking about sort of citations and how can we, okay, we found that there's an inflection point, we have this summary, or we have this little extraction that's come out. Well, where did it come from, and how can we look into this a little bit further to give us some more confidence, and maybe flesh things out a little more. I'll also mention, and sort of to kind of now give some broader context in terms of where we can head with this and how we're sort of thinking about how this can be used. We need to bring in other data sets as well. And so we've got sort of this open source aspect, right, that focuses on pretty high level type topics, and starts to get into, some of the details. It's fairly detailed depending on whether you're looking at news or whether you're looking at Twitter. And of course, the different news publications are a little bit different. But when we start thinking about sort of like all of the things that go into building a nuclear reactor, there's also a lot of representation in the literature that we can look into. And so this pipeline could also be applied in such a way where if you were to just go to PubMed, for example, you get sort of these citation metrics or journal publication metrics, right? And you get this temporal profile. In this case, I've just typed in sort of the generic example of nuclear physics, right? And so we're looking between 1932 and 2024. There's representation in this particular database. And then over here on the right-hand side, I've basically just taken that temporal profile and I've turned it onto a log scale so that you can see a little bit better how this changes across time. But essentially, the point here is that you have sort of these built-in inflection points across time. And so something has happened within the literature or the interest in a particular topic that has caused that inflection point in the number of publications that are coming in. And so how can we sort of figure out what would be going on there? And so, of course, over here on the left-hand side of the plot, closer to the 30s, nuclear physics is really, kind of at its infant stages, right? We're sort of just starting to come up with it. And so we've got sort of the general theory and sort of overview type papers of what's going on in the field, but we're really talking handfuls of publications for the first 10-15 years of time. Then you go into sort of this second window. I've sort of manually marked where there's sort of an inflection point in the number of publications. And you see that you have things like nuclear physics uses in medicine, and you have expanding theoretical work starting to get more and more niche. You've got accelerators that are being built and talked about, and technologies that can come from using accelerators. And you're also having a lot of conversation about sort of nuclear arms. Then as you come to that third inflection point, you see you've got, all of a sudden the advent of computers and their widespread use and how they can be applied and help us out more and more in this field. And again, sort of increasingly niche applications across the entire thing. So essentially the point here is that this is pretty easy to do if you're looking at sort of the early stages. 10 publications you can look at. You can just look at the titles and you can pretty well understand what's going on in a field. But as you sort of increase these number of publications, you have all sorts of more things that are going on, and it becomes essentially impossible for you to scroll through all of those and come up with the number of topics that you could look into. All right, so what if we want to do this across very specific fields of say some chemistry activity, or we wanted to look into different remediation activities that we could perform across the Department of Energy complex? There's lots of sort of disparate or seemingly disparate science that goes on, basic and fundamental research that may have real world applications, but we have to sort of connect all of those dots together to understand that technology is there. So that's kind of the key point here. You could do this across multiple topics. You could really bring things together. And now all of a sudden you're starting to sort of fill in some of these gaps and understand how you can sort of grow and evolve certain, scientific disciplines and come up with new technologies and all of this kind of stuff. So we're thinking about, and we have some proposals in with EM to do this, fusing both sort of the open source data as well as publications coming from, say, OSTI or other locations within the government, where we can sort of understand all of the different activities at all of the different DOE sites, what technologies have been applied, what might be transferable to other locations, and how can we use that. But again, it really comes down to and especially in a time like this where we're losing a lot of the people who have been here for decades. How do we retain this knowledge and then pass it on, and also continue to develop new techniques and technologies as we continue on with our DOE missions as well? So that's what I wanted to kind of highlight here in terms of how some of these techniques can potentially be applied. And so with that, I think I'm at 51 or so minutes here. So I'm going to go ahead and just kind of leave this up here. I've kind of already summarized the conclusions as it is, and I would just thank you all, and happy to answer any questions you might have.
Tom, thank you for this fascinating research that you able to share with us. Before we continue with questions, I want to just remind people that
Oh, I lost audio.
sorry, can you hear me? Can you hear me now?
Yes.
Okay, sorry. I don't know if you caught anything I said before. I was going to say that thank you for your fascinating presentation, Tom. Before we continue on question, I just want to let people know that I posted the link for the feedback form in the chat so people can answer, provide their feedback on the presentation. But I want to open up to the attendees for questions, because this is fascinating research, and I'm sure there are questions out there. Can you guys hear me okay?
Yes.
Hi, Tom. This is Himanshu. First of all, excellent presentation and a lot of research activities around NLP, and especially focused on fundamental algorithms. There was kind of interesting. So my question is, there are two questions actually. One, what kind of infrastructure you have used to process this large amount of data?
Yeah, good question. So one of the key things here was we didn't want to bring in all this open source data to our site computers or to government resources, because you never know what's inside of it, right? And so, and especially when you're working with things like Twitter, no matter how much you filter, you wind up finding the depths of Twitter in your data sets. So we have this collaboration with Virginia Tech. We've been using some of their Amazon AWS resources, and honestly, I don't know all of the specifics there, but it's not that that hefty of a system that we have. We've sort of started playing around with some GPUs as well. We haven't used those very heavily yet at this point, but I would say that that's a very key consideration for us, and I know that that's also going to be of high interest to NA22 coming into their call for FY25 will be coming out here pretty soon, and they're going to be pretty interested in systems and how we can sort of set up these big data type problems. So training and a lot of this pipeline is very, very computationally expensive, and so we've been doing a lot of it. We may use 16 processors or something like that to try to train word embedding models a little bit faster, but we haven't really gotten a whole lot into the software architecture aspects, the hardware architecture aspects, but it's something that we definitely have to consider, and especially as we sort of start to look for end users as well. So good question. I know I didn't give you much of an answer there. I don't know a lot of the specifics. If you start talking about cloud architectures and hardware and all of that kind of stuff, I'll be lost pretty quickly. So I leave that to other people.
Right. Thank you, Tom. The other question I have, as I see, like you're using Jaccard similarity, cosine similarity, and stuff like that. Is there any interest in exploring the pre-trained model to kind of do this kind of analysis, which are currently like very popular in LLM?
Yeah. So there definitely is interest. So we've been using mostly the word-to-vec algorithm for finding the actual inflection points, and the key reason that we've been doing that is simply sort of this idea of comparing contextual versus non-contextual language models. So where some of your large language models, they're maybe not quite as focused on they're capturing broad context, whereas something like word2vec is capturing a very narrow context, and it's actually not even built in there at all. It's giving you a representation of a term, so it's a non-contextual model, and that actually seems advantageous to us in terms of actually finding these contextual shifts, because it's just giving us a simple representation of that word at that point in time. Now we did think about using transformer-based models coming into this next work. But it seemed like quite a lot of effort to sort of take the pipeline and then change sort of that key step in terms of the actual embedding model. So we've been instead using those a little bit more on the back end. But I do think that there are quite a number of applications where large language models would be applicable here. And I'll also mention that they've been of high interest to NA22, who's funding this work, and they have some pretty large venture projects that are looking into not just large language models, but foundation models in general. So,
right, thank you. I just want to share with you that we do have at FIU a big interest in this area, and of course, you mentioned Alejandro worked with you on this project. In fact, we are exploring all the different modeling options, starting from pre-trained model to kind of model augmentation for fine-tuning of that, or even coming up with a custom model. So we are looking, we are getting different projects where this interest is of the client. And we are, as we speak, in fact, we are exploring all different options, and we are having a lot of challenges as far as the resources are concerned because of the number of like billions of parameters that exist in the LLMs. And so the team is working kind of to find out like how do we bring the model in FIU environment and fine tune that with the D&D knowledge management system. That's the one we have here. And of course, we are open to other opportunities as well. So I just want to share that we'll be very happy to collaborate if there is an opportunity in this. And we are building a lot of experience here at FIU in this area.
Yeah, that sounds great, and it's it's been great working with you on Ultimus and some of these other things. And Alejandro did a great job over the course of the summer. And what I'm finding is that this particular topic, although we've been using it in sort of non-proliferation space, I think it's really taking off, and a lot of people are from a lot of different fields are becoming more and more interested in how can they use language models to sort of do these types of things. So I think there's a lot of opportunities coming up in the future. So happy to discuss those more.
Sure. Thank you. Thanks, Tom. Anyone else has any other question? Please go ahead and ask.
Well, if there's no more question, Tom, I just want to thank you for your time. Thank you for the great research presentation. I do have a question, actually. You were showing data back from 2014, 2015. So are you going to go back beyond that? And I know Twitter, is recent data, but the Department of Energy and nuclear talks been going on before that. So are you going to go back, maybe using OSTI or some of those documents, or how are you going to fill the gap if you go back? What sources of data are you going to be using?
Yeah, absolutely. So the key thing here is that I think the system is pretty much amenable to any data source that you would want, and so we're pretty it's agnostic to how much time you want to cover or anything like that. So I'm interested in even something like now granted there's not enough data necessarily here to train any meaningful embedding models if you're looking in the 30s at nuclear physics, but open to going as far back in time as what we possibly can for a particular topic. We're open to all data sources. At this point, we're very well set up just for text. So as long as we can curate something, we'd be interested in whatever time frame we have. So yeah, in terms of OSTI and some of the EM type scope that I had mentioned of where we're looking to apply this. In many cases, I think we would want to capture as much of the site history, which again, across the DOE, we're going back to, Manhattan Project times. We would want to capture as much of that as what we possibly could, I think, to understand and to build into these models sort of the context of everything that has gone on so that we can understand then the downstream sort of environmental impacts that we would be interested in. So we're open to as much time as what we possibly can capture.
No, it's awesome. Thank you.
One
Any other?
second. So Tom, yeah, one quick question. So Tom, are you planning to present this research in waste management? Because this can be a fantastic talk there, actually.
So I'm not planning on presenting this there, but what I will say is that Alejandro, I know, is taking a poster down there, and he'll be touching on it. So I'll be certainly interested to hear some of the feedback that comes, and we've been thinking for quite a while. I've been asking around or sort of shopping around sort of ideas for EM, and I think those are kind of starting. And so within the next couple of years, I think you might wind up seeing something similar, but outside of non-proliferation space, more in EM space that pops up at waste management.
All right, thank you.
Hi, Tom, one more question. I'm sorry. How responses are these models? You gave the example at the end there, when you were giving the example about, Russia doing nuclear talks with Argentina, for example. When you see a threat that you want to pull, how responsive is it for you to go ahead and pull that thread? I mean, how much time does it take to get new results based on the new data that you receive?
Yeah, that's a great question. So it takes probably a couple of hours at this point, I would say, to kind of filter through that, depending on which of the techniques that you're using. But so much of this relies on sort of, well, in many cases, this relies on having some things that are pre-computed, which are a little heavier, right? So if I wanted to train all the embedding models, right, that might take me a day or a couple of days. And if I want to build out some of these graphs, and especially if I want a lot of nearest neighbors and a lot of ranks in those graphs, that's a pretty expensive task right there. So that can take a few days. But actually going in and pulling the data out, it maybe would be a couple of hours, but it's actually it's fairly quick. So again, this sort of the software architecture and the hardware architecture, that's something I think we really have to think through as we start finding end users. But for the most part, that the information retrieval aspects are fairly quick.
That's awesome. Well, Tom, thank you very much. Once again, thank you for your time. Thank you for the presentation. This is Dr. Tom Danielson from Savannah Rio National Laboratory. And once again, thank you for those who attended. Our next Tech Talk is going to be January 16, 2024. So remember to fill out the feedback form in the chat, and we'll see you then. Thank you for your attention.
Thank you, Tom.
Goodbye.
Bye-bye.
Thank you all.
Thanks.
Yeah, it was great.
Mhm.